When we left off, we were looking at these two different definitions of a function we were calling p. And the thing that we notice about these two different definitions is that they have different domains. The first formula applies for values of w that are less than 5. And the second formula applies for values of w that are greater than or equal to 5. And that's important. The thing that we notice most about these domains is that these domains do not overlap. They're what we call disjoint. Disjoint literally just means they don't overlap each other. That's important because that means that for any particular value of w, only one of these applies. When we have this situation, we can take these two functions and essentially tape them together in order to make a new function. This is what the tape looks like. We write p of w once equals here we have the same kind of curly bracket that we use when we write, for example, a system of equations. Our formulas lined up vertically, then the word if also lined up vertically, and then the domains. And the way that we read this is literally as these two just stuck together. If we wanted to evaluate this function, for example, for the number 2, so if we wanted to take p of 2, remember that that's plugging in w equals 2. First, we plug it into each of the rules on the right here. We see that this first inequality is true, while this second inequality is false. So that tells us to use the first expression for p. The first inequality is true, so we use the first expression. Thus, p of 2 is 8 times 2 is 16. If we wanted to evaluate p of 6, we see that, well, 6 is not actually between 0 and 5, but 6 is greater than or equal to 5. The second inequality is true, so we'll use the second expression. That is, we'll use 7w. Thus we have p of 6 is 7 times 6 is 42. Let's see one more. Suppose we're asked to evaluate p of negative 4. Something strange happens now, right? When we plug in negative 4, both of our inequalities are false. Negative 4 doesn't follow either of these rules. It isn't in either of the pieces of the domain. What does that mean? Well, negative 4 is just not in the domain of p. That is, p of negative 4 is undefined. If we have a number that doesn't follow any of the rules, then that number is just not in the domain of the function. Let me give you one of these to try. Try evaluating this function f at each of these values. Pause the video and try this now. Okay, so the first thing that we do with each number is see which inequality it makes true. For this first example, we see that, well, 1 is less than 2. So we'll use the first rule. So f of 1 is 2 times 1 minus 1 equals 1. How about 2? Well, 2 is not less than 2. Oh. Two fits into the second inequality. Right? 2 is less than or equal to 2. That's true. So we'll use x plus 1. We get f of 2 is 2 plus 1 is 3. How about 2.6? Well, that also fits the second inequality. Certainly 2.6 is between 2 and 3. So again, we'll use x plus 1. F of 2.6 is 2.6 plus 1 is 3.6. How about negative 2? Well, negative 2 is less than 2. That's fine. Notice this function is defined for negative numbers just fine, because all the negative numbers are less than 2. So we'll use that 2x minus 1 formula again. F of negative 2 is 2 times negative 2 minus 1. We can use a calculator for this if we'd like. We get negative 5. What about 7? 7 is not less than 2. It's not between 2 and 3. Oh, but it is between 3 and 10. So that means we use that third expression. So f of 7 is 7 squared. That's 7 times 7 is 49. Again, we can use a calculator for that if we'd like. And finally, what about 42? 42 is not less than 2. It's not between 2 and 3. It's also not between 3 and 10. All of the inequalities are false when x is 42. Therefore, f of 42 is undefined. 42 is not in the domain.